In the summer of 2004, from a telescope on a mountain in the Arizona desert, 3 astronomers found something that had been drifting through the inner solar system for 4.5 billion years without a single instrument having noticed it. In 48 hours, they knew what it was. In 6 days, they wished they didn't. The impact probability was 2.7%. Date: the 13th of April, 2029. A Friday, the highest number ever formally assigned to a near-Earth object in the recorded history of solar system science, confirmed independently by 3 separate research teams within the same week. Tonight, we'll follow this rock from the night it was first seen to the April night in 2029, when 3 billion people will be able to watch it cross the sky without a telescope, and we'll find out what 17 years of calculation, 1 spacecraft, and a 600-meter corridor in space changed about everything. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. The night of the 19th of June 2004, at Kitt Peak National Observatory in the Sonoran Desert of Arizona, was a survey night, indistinguishable in the moment from the hundreds of nights that had come before it and the hundreds that would follow. Roy Tucker, David Tholen of the University of Hawaii Institute for Astronomy, and Fabrizio Bernardi from the Observatoire de la Côte d'Azur were running the Spacewatch telescope across sections of the ecliptic plane, the band of sky where the solar system's debris concentrates along the ancient flattened disk of its formation, letting the automated detection software flag anything that moved against the fixed stars behind it. The work is patient and repetitive by design. The telescope sweeps a section of sky, waits a few hours, sweeps the same section again, and compares the 2 images for objects that have shifted position. Most flags resolve immediately into known objects, already catalogued and accounted for. Most of the remaining flags dissolve on the next pass. Brief artifacts of instrument noise or cosmic ray hits that a second image confirms were never there at all. Survey astronomy generates false positives constantly, and the system is built to separate them from real detections with a minimum of wasted follow-up time. What Tucker's data returned on the night of June 19 was a magnitude 19.7 point source, faint enough to be invisible to any unaided eye, moving along a path consistent with a near-Earth asteroid in the inner solar system. The provisional designation was assigned 2004 MN4, and the early tracking began. The error ellipse, the probabilistic cloud that contains all trajectories consistent with the available observations, was wide in the way all early asteroid determinations are wide, not alarmingly so, just ordinarily uncertain, the standard condition of a body seen for the first time without any prior observation history to constrain it. Fabrizio Bernardi began a precovery search, looking through the Spacewatch archive at Kitt Peak for earlier photographs of the same region of sky that might show 2004 MN4 in a position before the June 19 discovery night, unrecognized and uncatalogued, waiting in the existing data for a discovery that would make it relevant. This kind of archival detection can dramatically extend the observation baseline for a newly discovered object, adding months or years of additional position data without requiring any new telescope time. Bernardi found what he was looking for: a plate from the 15th of March 2004, 3 months before the official discovery night, showing the asteroid faint and unmarked in data no one had yet thought to check. He incorporated the precovery position into the orbital calculation. Extending the baseline narrows the error ellipse. More data, tighter constraints, a better orbit, the refinement running in one direction as it always does when new information arrives, away from uncertainty and toward a stable solution. Bernardi ran the numbers. The error ellipse did not narrow away from the Earth. It narrowed onto it. David Tholen, who had spent decades working near-Earth objects and had developed the particular composure that years of false alarms and quiet resolutions builds in a scientist, looked at the result. Later, in interviews, He would describe the moment with the precision of someone trained to say exactly what had happened. "The orbit was correct," he said. "The orbit was inside the Earth." He had never computed anything like it. He looked at the screen for a long moment without moving, because there was nothing to do with that result, except verify it again. Something that old had never been seen coming. Until now. 2.7%. Written as a fraction, that is approximately 1 in 37, a number that in most everyday contexts would not register as alarming. Smaller than the odds of rolling any particular combination twice in a row with a standard pair of dice, smaller than most risks that receive sustained attention in ordinary life. But the number does not live in an ordinary context. And the comparison that matters is not to dice or to daily life, but to the entire prior history of planetary defense, which had never once formally published an impact probability above 0.5% for any known near-Earth object in the decades since systematic tracking programs began. 2.7% was more than 5 times larger than anything the field had ever recorded. Donald Yeomans had been managing NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory in Pasadena long enough to have watched the standard resolution sequence many times. Discovery, initial uncertainty, a spike in probability, additional observations, the probability collapsing towards zero, quiet resolution. He had developed the institutional steadiness that this pattern, when it runs correctly, eventually rewards. When his team calculated the initial probability in late December 2004 and found 1.6%, he waited for more observations, as he always did, because that is what additional data does. On December 23, with more data folded in, the calculation was repeated. The probability was 2.7. It had not collapsed. It had grown. Yeomans and his colleague Paul Chodas published the numbers. The European Space Agency's Near-Earth Object Coordination Center in Frascati, Italy, running its own independent calculations on a separate dataset with a separate computational pipeline, arrived at the same figure within the same week. The team behind NEODISE at the University of Pisa confirmed it independently. 3 institutions, 3 methods, 1 answer. The Torino Impact Hazard Scale, the communication framework created in 1999 by Richard Binzel of MIT, designed to translate asteroid risk across the gap between scientists and the public, numbered from 0 to 10, assigned the object a level of 4. Level 4 means, in the scale's careful language, that the object merits close attention from astronomers. That level had never been reached before in the scale's history. It has not been reached since. The date those 3 independent teams were converging on, the date attached to this record-breaking number, was the 13th of April 2029, a Friday. The 13th. No physicist treated the calendar coincidence as meaningful, because orbital mechanics is indifferent to the day of the week, but no one forgot it either, in the quiet spaces between calculations and official statements, because certain juxtapositions have a way of staying in the mind, even when the mind is trained to distrust them. The name came from mythology, and the choice was more accurate than anyone at the time understood. Roy Tucker submitted the naming proposal through the International Astronomical Union's standard process, and the name chosen was Apophis, Pi Omicron Phi Iota, Ceph in Greek, derived from the ancient Egyptian Apep, the chaos serpent, the primordial monster, the adversary of Ra, whose nightly purpose was to swallow the sun before it could complete its journey and to unravel the order of creation back into the void that preceded it. In Egyptian cosmological thought, Apep is not a threat that was defeated once and disposed of. The serpent returns every night, without exception, to attempt the same destruction it attempted the night before, and the survival of the ordered world depends on the same battle being won again and again, indefinitely. The name was not chosen frivolously. No asteroid name is. But people in the planetary defense community would note, in the years that followed the initial alarm, that the mythology was structurally more accurate than even the namers had intended. Not because the asteroid would devour the Sun, but because the problem it posed did not have a single calculation that disposed of it permanently. The 2029 impact was cleared, but the clearing revealed a keyhole for 2036. When 2036 was eventually constrained, a 2068 scenario needed attention. When that was resolved in 2021, the question of what the post-flyby orbit would look like in the centuries beyond remained open, pending measurements that only the flyby itself could provide. The serpent, as the mythology had it, comes back, and the test is never finished. Apophis is, among its many distinctions, the first asteroid to demonstrate this property clearly enough that the field could study it in detail. The way that clearing one date redirects the problem rather than ending it, and how the long-term question of whether a rock will intersect your planet is not a single calculation, but a continuing process, requiring new measurements at each stage. On the 30th of June 1908, a small object from space entered the atmosphere above the Podkamennaya Tunguska River basin in Siberia and exploded at an altitude of roughly 8 to 10 kilometers before it could reach the ground. No crater was formed because the object, estimated at approximately 50 to 80 meters in diameter, was fragmented and vaporized by the atmospheric pressure and heat before impact. What reached the ground instead was a pressure wave and a thermal pulse. 2,150 square kilometers of boreal forest were flattened over the following seconds and minutes, an area roughly the size of the city of Los Angeles, and the trees at the epicenter were stripped of branches and left standing only as charred poles pointing skyward, not knocked over by the blast wave, but preserved in place by the vertical descent of the pressure from directly above. The Tunguska event released energy estimated at 10 to 15 megatons of TNT equivalent. No human fatalities were recorded, because the Siberian basin where the explosion occurred was essentially uninhabited at the time. If the same object had entered the atmosphere 3 hours earlier, over a slightly different longitude, accounting for Earth's rotation, it would have detonated above European Russia. If it had entered a few hours later, it would have been over Western Europe. The Tunguska impactor was roughly 50 to 80 meters across. Apophis is 340 meters. The kinetic energy scales with the cube of the relevant dimension and with velocity, and the result, carrying through the numbers, is that an Apophis scale impact event would release energy between 25 and 100 times larger than Tunguska, depending on composition, entry angle, and whether the impact occurs on land or ocean. A land impact would excavate the crater described earlier. An ocean impact, which the probability distribution of Earth's surface makes statistically more likely for any given asteroid, would produce ocean waves that would travel across entire basins, arriving at distant coastlines at heights that depend on ocean depth and coastal geometry. But that historical analogue suggests would be devastating across a regional scale. Tunguska is not ancient history as geological timescales go. 116 years ago, a rock that would not even be large enough to make the potentially hazardous catalogue detonated above an inhabited continent and leveled forests across an area the size of a major city. The Apophis problem is not abstract. 340 meters. Most people, holding that number, reach for something they have stood beside. The height of the Chrysler Building, or 3.5 soccer fields laid end to end, or about the length of 3.5 city blocks compressed into a single drifting mass. These comparisons are all arithmetically accurate, and none of them captures what 340 meters means when it is moving at 7.4 kilometers per second toward another body. At hypervelocity, the regime above roughly 3 kilometers per second, where the behavior of matter changes in ways that have no analogue in ordinary experience, rock stops behaving like rock. The shock wave generated by the collision exceeds the compressive strength of any material that exists. And both the impactor and the target briefly enter a state where they flow like fluids, not metaphorically, but physically, measurably, in the way that laboratory experiments reproduce and that planetary impact simulations depend on. The impactor does not punch a hole through the target and come out the other side. Both objects are transformed in the first fractions of a second. The impactor vaporized, the target surface melted and excavated outward in a bowl whose diameter is 10 to 20 times the diameter of the impactor itself. For a 340-meter asteroid striking a land surface at 7.4 kilometers per second, the resulting crater would be 3 to 5 kilometers across. The standard comparison in this kind of modeling is Barringer Crater in Arizona, which was formed by an iron meteorite approximately 50 meters in diameter and is 1.2 kilometers wide and 170 meters deep. The meteor crater impactor was roughly 50 meters. Apophis is roughly 340 meters. Kinetic energy scales with mass, and mass scales with the cube of the relevant dimension. An object with 6.8 times the diameter carries not 6.8 times the destructive energy, but approximately 315 times the energy of the meteor crater event once density and velocity are carried through the calculation. Planetary defense scientists use the word regional for what Apophis represents in an impact scenario. Not global, not extinction level, regional, which in the field's technical vocabulary means an event capable of destroying a metropolitan area and its surrounding territory, releasing energy in the range of 1,000 to several thousand megatons of TNT equivalent, and generating, in the statistically more likely ocean impact, tsunami systems affecting coastlines across entire ocean basins. The word is precisely accurate. It also requires a specific effort to hold at its actual scale. Regional means a city, with specific streets and specific populations. Regional means a coast. Regional means something close and concrete, in a way that extinction level somehow does not demand the imagination to confront directly. The 2.7% probability was attached to this word. This energy, this scale. The Torino Impact Hazard Scale was created in 1999 by Richard Binzel, a planetary scientist at MIT, specifically to address a communication problem that had been building as the Near-Earth Object Survey programs found increasing numbers of asteroids and began assigning impact probabilities to some of them. The problem was this: scientists calculating impact probabilities have a precise, probabilistic language for what those numbers mean, but the general public does not share that language, and the result of releasing a non-zero impact probability without a calibrated framework for interpreting it was predictably bad. Alarm when the probability was routine, confusion when it changed rapidly as new observations arrived, and a general difficulty distinguishing meaningful concern from noise in the catalogue. Binzel designed the Torino Scale as a communication tool, not a scientific one. It runs from 0 to 10, with each level corresponding to a specific combination of impact probability and impact energy, and with plain language descriptions calibrated to the level of attention appropriate at each point. 0 means no hazard, no attention required, the standard state of essentially every catalogued asteroid. 1 means a close encounter, meriting monitoring. 2 through 4 represent increasingly concerning close encounters warranting increasing levels of attention. 5 through 7 describe scenarios that warrant serious concern and potential planning. 8 through 10 represent certain or near certain impacts, differentiated only by the energy involved. Level 4, where Apophis was assigned in December 2004, sits in the range that says a close encounter merits attention by astronomers, and explicitly notes that the probability is not negligible. Level 4 is the first level at which the scale's language shifts from no cause for public attention towards something more serious. The first level at which an object genuinely deserves to be watched, with the expectation that it might remain concerning as more data arrive. No object in the catalogue had reached level 4 before Apophis. No object has reached it since. The scale had been in operation for 5 years when Apophis arrived at level 4 and stayed there for 6 weeks. which was the longest any object had held the rating. After Apophis was cleared of the 2029 impact scenario, it was reclassified to Level 1, a close encounter still worth monitoring, reflecting the 2036 keyhole probability, and eventually downgraded to Level 0 after the full suite of observations and calculations brought the impact probability for all dates to 0 or near 0. Level 0 is where it sits today, where it will remain until the April 2029 flyby itself, and where it is expected to remain after the flyby, once the post-encounter orbital determination is complete. Level 0 does not mean forgotten. It means the problem is solved at the scale the current data can resolve. Survey astronomy is, at its core, a counting problem, one that was far from solved in 2004. The inner solar system contains a population of near-Earth asteroids, objects whose orbits bring them within 1.3 astronomical units of the Sun and into proximity with Earth's orbital path, estimated at roughly 25,000 objects larger than 140 meters in diameter. Of those, the survey programs operating in 2004 had found and catalogued approximately 40%. The rest were known to exist statistically. They had to be there, given the size-frequency distribution of the known population, but had not yet been individually identified, tracked, or assigned orbital elements. The Spacewatch program that discovered 2004 MN4 was one of several running at the time, each covering different portions of the sky on different schedules with different equipment. Catalina Sky Survey in Arizona, Linear in New Mexico, NEAT operating from Palomar and Mauna Kea. The combined network swept the accessible sky repeatedly, searching for moving objects, flagging candidates, submitting confirmed discoveries to the Minor Planet Center at Harvard-Smithsonian, which maintains the authoritative catalogue. The limitation all ground-based programs share is geometry. They observe at night, from the surface of Earth, looking outward into the sky, away from the Sunday, objects that spend most of their orbits in the sunward direction. Between Earth and the Sunday are difficult or impossible to observe from the ground at most phases of their orbit, because they appear close to the Sun in the sky, lost in the brightness, inaccessible during the hours when observation is possible. The Aten family of near-Earth asteroids, the orbital class to which Apophis belongs, tends to spend significant portions of its orbit in exactly this sunward blind zone. Apophis had been circling the Sun on its 323-day orbit for 4.5 billion years before the night of the 19th of June, 2004. It had made millions of trips around the solar system. Some of those passages brought it within detection range of every survey telescope that ever existed on the ground, for months at a time. Had those telescopes been pointed at the right section of sky, the Spacewatch survey on June 19 was the first time the geometry of the asteroid's orbit, the coverage schedule of the detection program, and the conditions of the night aligned in a way that produced a positive detection. 4.5 billion years of invisibility resolved in a single night. And what the data said, once the precovery was incorporated, was something no amount of careful language could soften. The 6 weeks between the December 23 publication and the late January 2005 observations were unlike any previous period in the history of planetary defense. The media response to the 2.7% announcement was substantial and, in some places, poorly calibrated to the uncertainty still attached to the number. A 1 in 37 chance that an asteroid will strike Earth is accurate as a statement of the December 23 orbital determination, but misleading as a headline because impact probabilities assigned to near-Earth objects in the first weeks after discovery are almost never final, and the standard expectation, built from decades of prior examples, was that additional observations would tighten the orbit and resolve the uncertainty in the asteroid's favor. The field had never before seen a probability this high, but the mechanism expected to clear it was the same mechanism that had cleared every previous alarm. Gather more data, tighten the orbit, watch the probability go away. What complicated the communication in those weeks was that the probability had not collapsed at the first refinement. It had grown from 1.6 to 2.7% when the precovery was added. Scientists at JPL, ESA, and PISA tried to explain that this growth was an artifact of the orbital determination improving, and that the number was expected to change significantly with the next round of observations. But a probability that has just grown in response to better data is not easily framed as probably resolving towards zero, particularly when the honest answer was that they did not yet know exactly which way it would go. In January 2005, observations from multiple telescope networks, the Spacewatch facility, the Observatorio Astronómico Nacional in Spain, and several others, provided the additional data the December calculation had needed. The trajectory was refined. The 2029 impact scenario collapsed. The probability for a direct collision on the 13th of April 2029 fell to something indistinguishable from zero. The immediate alarm was over, but what the same orbital refinement also produced, for the first time, was an accurate estimate of the minimum approach distance during the 2029 flyby. And that number changed the nature of the Apophis problem entirely. The orbital determination of any near-Earth asteroid is not a single number. It is a probability distribution, a cloud of possible positions and velocities at any given moment, each consistent with the full set of available observations and their measurement uncertainties. Weighted by likelihood, the center of that cloud, the most probable position, is what gets reported as the orbit. But the cloud itself, the full extent of the uncertainty, is what gets used for impact probability calculations. This cloud is called the error ellipse, and it has a specific shape at any given time. In the first days after a discovery, when only a handful of measurements exist, the ellipse is large and elongated. It extends far along the direction of the asteroid's motion. Because position is much more tightly constrained by the geometry of early observations than velocity is, and small uncertainties in velocity accumulate into large uncertainties in position over the following months and years. As more measurements arrive, the ellipse shrinks. New observations provide new constraints, each one reducing the range of trajectories consistent with all the data combined, until the ellipse becomes small enough that its overlap with the Earth, or lack of overlap, can be determined with confidence. The 2.7% impact probability of December 2004 was precisely a statement about the error ellipse, the fraction of the probability distribution, the fraction of the cloud that intersected the Earth on the 13th of April 2029. 2.7% of the possible trajectories consistent with all available data at that moment led to an impact. The other 97.3% did not. Which set of trajectories contained the actual trajectory of Apophis was unknown. As additional observations arrived through January 2005 and the ellipse shrank, the fraction of the distribution that intersected Earth on that date dropped to zero, not because the actual trajectory had changed, but because the estimate of it improved, and the new estimate fell outside the Earth intersecting region. The probability went to zero not because the asteroid moved, but because the knowledge of its position became precise enough to see where it actually was. This is why the standard behavior of asteroid impact probabilities, rising briefly after discovery, then falling as more data arrives, is not random or arbitrary. It reflects the systematic process by which the error ellipse shrinks, starting wide and often intersecting the Earth by pure statistical overlap with a large target, then narrowing until the actual trajectory is separated from the Earth's position clearly enough to report zero probability. Apophis was unusual not because the initial probability rose to 2.7%, but because the ellipse, when it shrank, did not move away from the Earth immediately. It moved toward it first, because the precovery image constrained the orbit in a direction that happened to intersect. The subsequent clearing was only possible when the January 2005 observations provided enough additional data to push the refined ellipse clear. 32,000 kilometers. That is the minimum approach distance of Apophis on the 13th of April 2029, derived from the best available orbital determination once the January 2005 observations were incorporated. For reference, the ring of geostationary satellites, the telecommunications relays, weather monitoring platforms, and navigation constellations that constitute much of the world's orbital infrastructure, orbits at approximately 35,786 kilometers altitude. Apophis will pass inside that ring. The asteroid will fly through the zone occupied by humanity's satellites between them and the planet below at 7.4 kilometers per second. No tracked near-Earth asteroid of this size had ever been documented at this range in the recorded history of observational astronomy. For perspective, the Moon orbits at an average distance of 384,400 kilometers. The April 2029 approach will bring Apophis to roughly 8.5% of the Moon's orbital distance, inside the lunar orbit by a factor of nearly 12. But the significance of 32,000 kilometers is not exhausted by how impressive it is as a record. It is also the number that governs every subsequent question about Apophis's long-term behavior, because what happens to a small body during a close gravitational encounter with a large one is determined almost entirely by how close the encounter actually is. And 32,000 kilometers is close enough that Earth's gravity will meaningfully alter the asteroid's orbital trajectory, changing its period, the shape of its ellipse, and the orientation of that ellipse in space, in ways that determine whether the post-encounter path is safe for the following century, or whether it threads a specific narrow passage that sends the asteroid back. The question of exactly where, within the remaining uncertainty of the orbital calculation, Apophis actually passes, is not merely interesting. It determines the asteroid's future. A close gravitational encounter reshapes the orbit of the smaller body. This is not a special property of asteroid encounters. It is the ordinary behavior of any two massive objects passing near each other, understood mathematically since Newton, and worked out in detail for asteroid trajectories over the 20th century. The mechanism is this. As the asteroid approaches Earth, Earth's gravity attracts it, deflecting the incoming path. As the asteroid passes and begins to recede, Earth's gravity continues to act, pulling it back slightly. The net result of this continuous deflection through the encounter geometry is a change in the asteroid's velocity vector, both speed and direction. That accumulates into different orbital elements, period, ellipse shape, and orbital plane orientation, all shift by amounts that scale with the inverse square of the approach distance. At 32,000 kilometers, Earth's gravitational influence on Apophis is strong enough to significantly reshape the orbit, enough to alter the orbital period, enough to shift the ellipse, enough to reorient the trajectory in a way that produces a path substantially different from the one Apophis was on before the encounter. Whether the new path is safe or not depends on the precise geometry of the approach, and the sensitivity of that geometry to small changes in position at the moment of closest approach is the essential fact that makes the 2029 flyby complicated rather than simple. A difference of a few hundred meters in the position of closest approach, a tiny fraction of the total encounter distance, can produce a qualitatively different long-term outcome. In one region of the close approach geometry, the 2029 encounter places Apophis on a trajectory that drifts clear of Earth for the foreseeable future. In an adjacent region, just a few hundred meters away at the critical point, the encounter places Apophis in an orbital resonance that brings it back to Earth's neighborhood at a specific future date. That adjacent region has a name. It is called a gravitational keyhole. The concept of a gravitational keyhole was developed in its modern form by Paul Chodas of JPL in the late 1992, building on decades of celestial mechanics and resonant orbit theory. A keyhole is not a physical object. It is a mathematical region in the approach geometry defined as the set of possible approach positions through which an asteroid must pass in order for the subsequent gravitational deflection to place it in a resonant orbit that brings it back to Earth at a predictable future date. The defining counterintuitive feature of keyholes is that their width bears no relationship to the importance of what passing through them produces. A keyhole corridor may be a few hundred meters wide at the encounter distance, smaller than a city block on the scale of the full encounter geometry, and yet what happens on either side of it is qualitatively different. Pass through the corridor, and the orbit resonates, and the asteroid returns. Miss it by any amount, and the orbit drifts, and the asteroid does not return on that schedule. The line between these two outcomes runs through a passage whose size is often orders of magnitude smaller than the orbital uncertainty itself. For Apophis, the keyhole relevant to the most carefully studied post-2029 scenario was the corridor through which the asteroid would need to pass during the April 2029 flyby in order for Earth's gravity to place it in a specific orbital resonance, a resonance requiring Apophis to complete exactly 7 orbits around the Sun in the time Earth completes 6, which means that after 7 Apophis orbits and 6 Earth orbits, both bodies would be back in the same relative configuration that produced the 2029 encounter, except that the 2036 return, if the keyhole was threaded, would arrive at Earth intersection rather than near miss. This resonance is called 7 to 6. The width of the keyhole that leads to it was calculated by Chodas and his colleagues at approximately 600 meters. The 7 to 6 orbital resonance that defines the most closely studied post-2029 scenario deserves its own moment of explanation, because the concept of orbital resonance is one of the quieter and more counterintuitive results of solar system dynamics. A case where the solar system's geometry produces order out of what might seem like it should be chaos. Apophis, in its current orbit, completes one trip around the Sun every 323 days, moving along an ellipse that crosses Earth's orbital path twice per orbit, once on its inward journey and once on its outward journey. Earth completes one orbit every 365.25 days. Because the two orbital periods are different, the positions of Earth and Apophis relative to each other change continuously, and the two bodies encounter each other at different points in their respective orbits on different cycles. In most orbital configurations, this quasi-random variation means that close encounters between the two bodies are sporadic, occurring whenever the orbital geometry happens to bring them near each other at the same time, but without any systematic pattern. However, if the two orbital periods happen to have a specific ratio, if one period is a small integer multiple of the other, then the pattern becomes systematic rather than random, and the encounters repeat in a locked relationship. If Apophis were to complete exactly 7 orbits in the time Earth completes 6, both bodies would return to the same relative position every 6 years, and a close approach that happened this year would repeat in the same relative geometry. 6 years from now, the 2029 keyhole is the set of approach positions through which Apophis would need to pass in order for Earth's gravity to adjust the asteroid's orbital period from its current 323 days to exactly the value that creates this 7 to 6 resonance. The adjustment is small, a fraction of a percent, but the consequence is not small at all. It turns a sporadic encounter pattern into a systematic one, with Earth's position and Apophis's position locked into a relationship that repeats every 6 Earth years, and that, in the 7 to 6 scenario, brings the asteroid back to Earth intersection in 2036. This is why the width of the keyhole matters so much. Pass through it, and the orbital period is nudged into resonance, and the pattern locks. Miss it by any amount, and the period is not locked, and the pattern disperses. The line between resonance and dispersal runs through a 600-meter corridor. 600 meters. In the context of an encounter whose closest approach distance spans tens of thousands of kilometers, 600 meters at the critical point is not a meaningful fraction of anything visible on the scale of the geometry. It is a threshold whose existence is invisible unless you know exactly where to look for it. And in early 2005, the uncertainty in the Apophis orbital determination, the cloud of possible trajectories consistent with all available observations, was substantially larger than 600 meters at the point of closest approach. The question of whether the 2029 flyby would thread the 600-meter corridor could not be answered with the existing data. The initial probability that Apophis's actual trajectory fell inside the keyhole, and therefore that the 2029 flyby would set the asteroid on a return path for a 2036 impact, was calculated at approximately 1 in 6,000. John Giorgini, a specialist in precise orbit determination for small solar system bodies at JPL, had been working the Apophis calculation since the December 2004 alarm. He understood, in the specific technical sense of someone who had spent his career at the boundary of what instruments could resolve, exactly what was still driving the uncertainty. The error ellipse had been narrowed significantly by the January 2005 observations, but the remaining uncertainty was not purely a matter of getting more telescope time. It was being driven by a physical force acting on the asteroid continuously, quietly, invisibly, accumulating year after year into a drift that would eventually matter more than any other variable in the calculation. That force had a history as improbable as the asteroid itself, discovered by a Russian civil engineer who died in 1902 and published his findings in a pamphlet that almost no one read. Ivan Osipovich Yarkovsky was not an astronomer. He worked as a civil engineer in Russia, and in 1900 he privately circulated a pamphlet, not a journal article, not a submission to any professional body. Just a short self-published text distributed to a small private audience, in which he described a hypothesis about the long-term orbital behavior of small bodies under the influence of sunlight. The hypothesis was this: a small rotating body absorbs solar radiation on one hemisphere and re-emits it as infrared heat from a different hemisphere, because the rotation carries the heated surface away from the sunlit direction before it can release the absorbed energy. There is a thermal lag. The surface heats up over hours of exposure and cools back down only after that surface has rotated away from the sun, in the same way that the warmest part of a summer day arrives hours after solar noon, because the ground has been absorbing heat since morning and only reaches its maximum temperature well after the sun has passed its highest point. The result of this lag is that the momentum carried away by the asteroid's infrared re-emission is not symmetrically distributed around the incoming sunlight direction. It has a net direction set by the asteroid's rotation axis and period that produces a continuous gentle push, small per orbit, but accumulating over years into a drift that eventually separates the asteroid's actual position from where a purely gravitational model would predict it to be. The pamphlet was never widely circulated. Yarkovsky died in 1902. The hypothesis survived only because a single copy of the pamphlet was found in a library decades later by the Estonian-Irish astronomer Ernst Öpik, who mentioned it in a 1951 paper without developing it further. That passing mention was enough to preserve the idea from being completely lost. The effect Yarkovsky had described was independently rediscovered several times in the following decades, incorporated into planetary dynamics models in the 1,990 seconds, and received its first confirmed direct observational measurement in 2003 when Stephen Chesley and his colleagues at JPL published a paper in Science documenting the detection of the Yarkovsky acceleration in the orbit of asteroid 6,489 Golevka, measured to a precision that matched the theoretical prediction within the uncertainties. The Yarkovsky effect was validated as a real physical phenomenon in 2003. Apophis would be discovered 18 months later, and the validation of the effect in Golevka would turn out to be the methodological foundation for every key measurement in the Apophis story that followed. The Yarkovsky effect for Apophis specifically works through the same mechanism that Yarkovsky described in his 1900 pamphlet, but with numbers that matter in a very concrete way. Apophis rotates with a period of approximately 30 hours. A slow tumble, not the rapid spin of some smaller asteroids. The surface material, based on spectral observations from Earth, is consistent with ordinary chondrite mineralogy, the most common composition among stony near-Earth asteroids, with relatively low thermal inertia compared to metallic or water-bearing surfaces. Low thermal inertia means the surface responds quickly to heating and cooling. It warms up fast on the sunlit side and cools quickly as it rotates into shadow. The lag between absorption and emission is real but moderate, and the resulting asymmetry in infrared re-emission produces a force whose direction and magnitude can be modelled from those surface properties. For Apophis, this thermal push accumulates to approximately 170 meters of positional drift per year, not the distance the asteroid travels, which is billions of kilometers per orbit, but the lateral offset from the position a purely gravitational model would predict, building year after year as the sunlight continues to push. In absolute terms, this sounds negligible, but the 2036 keyhole is 600 meters wide, and the 2068 keyhole, which would emerge from the orbital calculation later, is narrower still. Over the years from the discovery in 2004 to the 2029 flyby, the accumulated Yarkovsky drift produces a positional uncertainty at the critical point of the close approach that is comparable to the width of the relevant keyholes. The Yarkovsky effect is not a secondary consideration in the Apophis problem. It is the dominant uncertainty. The surface properties that govern the Yarkovsky force are not exotic or mysterious. They are the same properties that determine how any rocky body responds to sunlight, and for Apophis, they can be estimated from ground-based spectroscopy even before OSIRIS-APEX arrives to measure them directly. Apophis belongs to the SQ spectral class, which corresponds in composition to ordinary chondrite meteorites, the most common class of meteorite to fall on Earth, with a mix of silicate minerals, small amounts of metallic iron-nickel, and low to moderate albedo. Its geometric albedo is approximately 0.33, meaning it reflects about a third of the sunlight that hits it and absorbs the rest. This albedo is moderate by asteroid standards, darker than the stony asteroids in the S complex that reflect closer to half the incoming light, and much brighter than the dark carbonaceous C-type asteroids like Bennu, which reflect as little as 4%. The thermal inertia implied by this composition is in the moderate to low range, consistent with a granular regolith surface, whose individual particles cycle through heating and cooling more quickly than a solid slab of rock would. These properties, folded into the thermal model, produce the predicted Yarkovsky acceleration, the fact that the 170 meters per year, measured directly from the optical residuals, agreed with the prediction from the surface property estimates, was itself a validation of the method. The two independent approaches converged on the same answer, confirming that the model and the measurement were both capturing the same physical reality. After the 2029 flyby, OSIRIS-APEX's thermal emission spectrometer will measure the surface temperature distribution directly, replacing the estimated thermal inertia with a measured one. The Yarkovsky model for the post-flyby decades will be built on those direct measurements, and the uncertainty that was the dominant driver of the pre-2021 impact probability assessment will be replaced with a directly constrained physical quantity. This is one of the reasons the scientific value of the OSIRIS-APEX mission extends far beyond the Apophis case itself. The methods validated at Apophis become the template for every subsequent potentially hazardous asteroid where the same question arises, and measuring the Yarkovsky acceleration precisely enough to resolve the keyhole question required, knowing quantities that no ground-based telescope could determine from a safe distance, the asteroid's thermal inertia, its bulk density, and the precise orientation of its rotation axis. These are properties of the physical surface and interior, not of the orbit, the first tool available for significantly tightening the Apophis orbital determination. And getting closer to the Yarkovsky measurement, the keyhole question required: was the Arecibo Observatory in Puerto Rico? Arecibo was, until its collapse in December 2020, the largest single-dish radio telescope on Earth. Its 305-meter dish, set into a natural limestone sinkhole in the hills of northwestern Puerto Rico, had been making planetary radar measurements of near-Earth asteroids for decades, achieving position accuracies of roughly 15 meters for close targets. Improvements of 1 to 2 orders of magnitude over what optical observations alone could provide. When Arecibo acquired an asteroid, the orbital determination typically improved in a single campaign by more than it had improved in the preceding years of optical tracking. In January 2008, Apophis made a moderately close approach to Earth, not nearly as close as the 2029 flyby, but within the range at which Arecibo could acquire the asteroid and generate high-quality range and Doppler measurements. David Tholen at the University of Hawaii, who had been part of the original discovery team and who had been monitoring Apophis continuously since the December 2004 alarm, organized and led the observational campaign alongside colleagues at JPL and coordinated multiple nights of radar operations. The 2008 Arecibo data reduced the orbital uncertainty for Apophis by roughly a factor of 100 compared to what optical observations alone had achieved to that point, a step function improvement of the kind that radar astrometry consistently provides. The team recalculated the 2036 keyhole probability with the new data folded in. The result? Approximately 1 in 45,000. The number had improved significantly from the 1 in 6,000 that the earlier determination had produced, but it had not gone to zero, and the reason it had not gone to zero was now clearly visible in the structure of the remaining uncertainty. It was dominated by the Yarkovsky effect. The radar had measured the position precisely, but the thermal drift was building on a trajectory that the position measurement could constrain but not fully resolve, because resolving it required knowing the surface properties of the asteroid, and the radar could measure the distance without measuring the composition, thermal inertia, or density that the Yarkovsky model needed. The 2036 scenario stood at 1 in 45,000, with the irreducible remainder driven by a physical force that no existing instrument could yet pin down. The 2008 Arecibo campaign produced something beyond the improved orbital determination, a preliminary shape model of Apophis derived from the radar data's Doppler cross-sections and the first reasonably constrained estimate of the asteroid's spin state. Radar data from a rotating asteroid contains information about the body's shape. As the asteroid turns, different cross-sectional areas face the radar beam, and the return signal's power and Doppler spread vary accordingly. By collecting this data across multiple rotation periods and multiple viewing geometries, analysts can fit a shape model to the variations, not with the spatial resolution that close proximity spacecraft imaging would provide, but sufficient to establish whether the body is roughly spherical or elongated, and to constrain the overall dimensions. The 2008 Arecibo data indicated that Apophis is modestly elongated, probably with long and short dimensions of roughly 450 and 170 meters respectively, and confirmed that the rotation period was approximately 30 hours, with a moderately inclined pole. The elongated shape has implications for the tidal interaction during the 2029 flyby. A sphere experiences a tidal force that acts symmetrically around its center, producing no net torque and therefore no change in spin. An elongated body, something more like a potato than a billiard ball, experiences a tidal torque. Because the tidal force on the near end is different from the tidal force on the far end, and if the elongation axis is not aligned with the Earth-pointing direction, the torque is not zero and the spin changes. Apophis's elongated shape, combined with the confirmed non-principal axis tumble, means that the tidal interaction during the 2029 flyby will have more rotational effect than it would have on a spherical body, and that the post-flyby rotation state will depend on the interplay between the tidal torque and the current tumble in a way that the models can estimate but not precisely predict without knowing the internal mass distribution. This is another measurement that OSIRIS-APEX will make directly, because the spacecraft can image the full shape at sub-meter resolution and track the rotation state continuously from the first days of its close proximity operations. Between 2008 and 2013, a second approach to the Yarkovsky measurement became available through an entirely different method. David Tholen's team at the University of Hawaii continued accumulating optical observations of Apophis between radar campaigns, building a positional baseline spanning years rather than months. Over a sufficiently long baseline with sufficiently precise individual measurements, the Yarkovsky acceleration imprints itself in the residuals of the orbital determination. The observed positions of the asteroid deviate systematically from where a pure gravity model predicts them to be, and the magnitude and direction of that deviation encodes the Yarkovsky force. Extracting this signal from the residuals requires statistical methods capable of separating the thermal component from the uncertainties in the underlying gravitational orbit. But with a long enough baseline and precise enough individual measurements, the signal eventually emerges. In 2012 and early 2013, Apophis made another moderately close approach, and Tholen's team used the opportunity to extend the positional baseline and attempt a direct statistical detection of the Yarkovsky acceleration from the optical data alone. The result was a positive detection, statistically significant, at greater than 3 standard deviations, with a magnitude consistent with the thermal models and a direction consistent with the rotation axis implied by the light curve. The thermal push was real, it was measured, and it was approximately 170 meters per year of positional drift, close to what the thermal models had been predicting, confirming that the models were in the right ballpark and that the key physical parameter driving the uncertainty was now, for the first time, directly constrained rather than only estimated. With this Yarkovsky measurement incorporated into the orbital determination, the team recalculated the keyhole probabilities. The 2036 scenario was effectively cleared. The best fit trajectory, including the Yarkovsky component, missed the 600-meter keyhole by a margin that reduced the probability to below 1 in a million. The 2036 impact was no longer a meaningful concern, but the same calculation that cleared 2036 revealed that a 2068 scenario required attention. The 2068 scenario is structurally different from the 2036 one, and that difference matters for understanding what had to be resolved. The 2036 scenario required a single link, the 2029 flyby threads, a specific keyhole, and the resulting orbit intersects Earth in 2036. The 2068 scenario requires a longer chain. The 2029 flyby reshapes the orbit in one specific way, producing a trajectory that leads to a second close approach in the early 2030 seconds. And that second encounter threads a different keyhole, placing Apophis on a path that arrives at Earth intersection in 2068. 2 keyholes, 3 close approaches. A chain of dependent outcomes that each requires a specific narrow passage before the chain leads anywhere. The probability of the full chain was approximately 1 in 150,000, small in absolute terms, but attached to a 340-meter asteroid, and therefore not dismissible without a measurement that could close it decisively. Closing it required knowing, with sufficient precision, whether the first link of the chain, the 2029 approach and its associated keyhole, was consistent with any trajectory in the current orbital uncertainty. The 2013 Yarkovsky detection had improved the calculation substantially, but the remaining positional uncertainty at the 2029 close approach was still larger than the keyhole corridor for the 2068 chain. The optical baseline could not reach the precision the question needed. What was required was another radar campaign, ideally as close to the 2029 flyby as possible, at the most sensitive facility available. The most sensitive facility available was Arecibo, and Arecibo was gone. The Arecibo Observatory collapsed on the 1st of December 2020. The primary support cable had shown signs of failure in August 2020, and engineering assessments after the first break concluded that the structure could not be safely repaired, that the risk of uncontrolled collapse during any repair attempt exceeded acceptable limits, and that the facility would need to be decommissioned. Before the controlled decommissioning could be carried out, a second cable failed, and in the early morning of December 1, the 900-ton instrument platform fell into the dish below, destroying both and ending the operational history of the largest single-dish telescope that had ever existed, a facility that had spent decades making the most precise asteroid position measurements available from the ground. For the Apophis story, the timing had an immediate practical consequence. The January 2021 observational window, when the asteroid would be within radar range at a distance that allowed high-quality measurements, was now a window that could not be covered by Arecibo. The only planetary radar facility still operational was the Goldstone Solar System radar in the Mojave Desert, specifically the 70-meter DSS 14 antenna of NASA's Deep Space Network, which had been making planetary radar measurements alongside Arecibo for decades. Goldstone was less sensitive than Arecibo for faint targets because its receiving dish is smaller and its transmitter less powerful. The question was whether, for Apophis, at 17 million kilometers distance in January 2021, not a close approach, but within radar range, the Goldstone capability was sufficient to achieve the measurement precision needed to close the 2068 question. Davide Farnocchia, a specialist in near-Earth object orbital determination at JPL's Center for Near-Earth Object Studies, led the team that would find out. The Goldstone observations of Apophis in January 2021 were taken over multiple nights, accumulating radar range and Doppler measurements through the full accessible geometry of the close approach window. The data were incorporated into the orbital determination alongside the complete observation archive that had been building since the 19th of June 2004. The discovery images, Bernardi's precovery from the 15th of March 2004, the full Arecibo radar datasets from 2008 and 2013, all optical observations accumulated over 17 years, and Tholen's Yarkovsky detection from the 2012 to 2013 baseline. The Goldstone measurements, combined with this full archive, provided something that prior analyses had been approaching, but had not quite reached: a radar dataset precise enough to extract the Yarkovsky acceleration directly from the residuals without relying on assumed surface properties. The thermal drift signal was there in the data, the systematic deviation of the observed positions from the purely gravitational prediction, at a precision that allowed it to be measured rather than modeled. The surface property assumptions that had been the limiting factor in all earlier determinations were no longer limiting. The data itself answered the question. Farnocchia ran the full analysis. The orbital determination that resulted placed Apophis's 2029 trajectory with sufficient precision to evaluate every relevant keyhole through 2116. None of them were occupied. No trajectory consistent with all available data, including the directly measured Yarkovsky acceleration, produced an Earth impact before 2117. The 2068 scenario was not reduced to a very small number that required continued monitoring. It was reduced to 0 within the measurement uncertainty. On the 5th of March 2021, NASA's Center for Near-Earth Object Studies published the result. Apophis was removed from the Sentry Impact Risk Table, the operational catalogue of objects with calculated non-zero impact probabilities. For the first time since the table's inception, 17 years after the initial alarm, for the first time since the night of the 19th of June 2004, the 13th of April 2029 was no longer a potential impact date. It was a close approach date, and nothing about the encounter had changed. The 100-year guarantee that the March 5 announcement established is a precise claim, and what it does not say matters as much as what it does. The announcement states that no orbital trajectory for Apophis, consistent with the March 2021 determination, produces an Earth impact before 2117. This is not a permanent or unconditional statement. It is a statement about the current precision of the orbital knowledge, and it extends exactly as far as that precision can reach. Beyond 2116, the accumulated uncertainty from the Yarkovsky drift, well characterized for the near term, but dependent for its long-term evolution on how the asteroid's rotation state changes, particularly during and after the 2029 flyby, begins to widen again, and the position distribution for the distant future eventually expands beyond the precision needed to confidently rule out all close approaches. This is not unique to Apophis. It is the honest limit of what any current orbital determination can establish for any near-Earth object over timescales of more than a century. Virtually no asteroid in the catalogue has impact probabilities reliably calculated beyond 100 years. What will extend the guarantee significantly is the 2029 flyby itself, and what the OSIRIS-APEX spacecraft will measure during it. Once the spacecraft has tracked Apophis through the close approach in real time, measuring the trajectory before, during, and after the keyhole period, with a proximity and precision unavailable from any ground-based instrument, the post-encounter orbital determination will be of a kind that no pre-flyby measurement can approach. Whether that extended calculation reveals anything requiring attention in the late 22nd century is currently unknown. The answer will arrive in April 2029 from a spacecraft that is already en route. The global network that has been watching Apophis since June 2004 is not a single coordinated system with a unified chain of command. It is an informal, distributed consortium of telescopes, institutions, and individual researchers who share data, update predictions, and coordinate observation campaigns through a combination of formal channels and decades of professional relationships. At the center of the data-sharing infrastructure is the Minor Planet Center at the Harvard-Smithsonian Center for Astrophysics, which receives positional measurements from all contributing telescopes worldwide, maintains the authoritative catalog of small solar system bodies, and publishes the combined orbital elements that feed into impact probability calculations at JPL and PISA. Observatories submit their measurements in standardized formats. The Minor Planet Center validates and archives them, and the orbital determination groups download the updated datasets and run their calculations. The system runs continuously. There is no single scheduled review, just a continuous stream of observations flowing in, being archived, and being incorporated into improved orbital solutions. The telescopes contributing to Apophis observations over the years have spanned an enormous range in size and sophistication, from the largest professional survey telescopes, Spacewatch, Catalina, Pan-STARRS, to smaller dedicated follow-up telescopes at observatories around the world that specialize in refining orbits for objects the surveys find. Individual professional astronomers at institutions in Spain, Italy, the Czech Republic, Australia, and elsewhere have contributed Apophis positions at various points in the 17-year observation campaign, each edition extending the positional arc and tightening the orbital solution. This is not unusual. It is the standard practice of the field, where the distributed global nature of the observation network is specifically an advantage because it means that coverage can be maintained across all celestial longitudes, even as the Earth rotates and any given telescope loses sight of a target. Radar observations, from Arecibo and Goldstone, are planned specifically as campaigns because the transmitting power required and the coordination between transmitter and receiver antennas require scheduling that the continuous optical network does not. These campaigns are organized months in advance, coordinated between the facility operators and the science teams, and represent the highest precision observations in the Apophis dataset by a substantial margin. The 2008 and 2013 Arecibo campaigns and the 2021 Goldstone campaign were the three events that most dramatically improved the orbital determination, each one producing an improvement that months or years of additional optical tracking would not have equaled. What this distributed, multi-institutional, multi-decade observation record represents is something that does not have a simple analogy. A sustained global attention paid to a single rock, maintained continuously for nearly 2 decades. Accumulating precision through the patient coordination of dozens of telescopes on multiple continents, ending with a spacecraft on its way to accompany the rock through the event that made all the watching necessary. In September 2023, a capsule entered Earth's atmosphere over the Utah desert and parachuted to a landing on the military test range at Dugway Proving Ground. Recovery teams waiting on the ground found it precisely where the trajectory prediction said it would be. Inside it, sealed in sample containers, was 121.6 grams of material from the surface of Bennu, a dark, carbon-rich near-Earth asteroid, approximately 500 meters in diameter, collected in a 10-second touch-and-go maneuver in October 2020 and carried across 6.2 billion kilometers of space over 3 years by the OSIRIS-REx spacecraft. The sample was the largest quantity of asteroid material ever returned to Earth by a NASA mission, and the early analyses revealed what the spectroscopic observations from the spacecraft's surface mapping phase had suggested. Bennu's surface is rich in carbon and water-bearing minerals, connected to the early chemistry of the solar system in ways that make it scientifically relevant for understanding how the molecular building blocks of living systems were distributed through the early solar system. The sample was distributed to laboratories across the world, and the science it enables will unfold over years. The spacecraft, after releasing the capsule, still had functional thrusters, working instruments, and enough remaining fuel, carefully managed across the years of the Bennu mission. To reach another destination, the mission team had been planning for this possibility, and they had identified the target before the capsule separation, and they had calculated the trajectory that would bring the spacecraft to that target in time for the encounter that no other human-made instrument would be positioned to witness. The target was Apophis. The spacecraft was renamed OSIRIS Apex, Apophis Explorer, and the new trajectory was confirmed. The trajectory OSIRIS Apex is following will bring it to Apophis in early April 2029, weeks before the April 13 closest approach. This timing is deliberate and essential. Arriving early gives the spacecraft time to observe the asteroid during the approach phase, while the tidal forces from Earth's increasing gravitational gradient are still building, and while the surface and rotation state are beginning to respond to those forces. The spacecraft will not arrive in time to watch a static object pass close to Earth and recede. It will accompany the asteroid through the most dynamically significant event in Apophis's recent geological history, observing continuously as that history unfolds. The instrument suite OSIRIS Apex carries is the same suite that characterized Bennu in detail during 2 years of close proximity operations, near-infrared spectroscopy capable of mapping mineral composition across the surface at high spatial resolution, a thermal emission spectrometer for measuring surface temperatures and deriving thermal inertia directly, stereo cameras capable of building 3-dimensional shape models at centimeter-scale precision, and a laser altimeter for high accuracy ranging to the surface. These instruments, at close range during the flyby period, will achieve something no prior asteroid mission has accomplished, characterizing the physical properties of a potentially hazardous asteroid, not in the abstract context of a routine scientific encounter, but in the context of the event most relevant to every question the planetary defense community has spent 2 decades asking about it. The Joukowsky acceleration, the bulk density, the surface composition, the rotation state evolution. All will be measured directly from a spacecraft that is physically there, rather than inferred from instruments separated from the asteroid by millions of kilometers and the limitations of what light and radio waves can carry back across that distance. The trajectory OSIRIS Apex, followed after the capsule separation from OSIRIS-REx, required a series of engine burns to adjust the spacecraft's orbit from the Earth return path to an interplanetary trajectory bound for Apophis. The mission team had designed this maneuver sequence before the capsule was released, accounting for the remaining propellant budget and the orbital mechanics that would bring the spacecraft to the asteroid before the April 2029 flyby. The spacecraft arrived at Apophis with enough fuel and operational margin to remain in close proximity throughout the close approach period, and for months afterward, mapping the post-flyby surface and tracking the post-encounter rotation state evolution as the asteroid recedes from Earth's gravitational influence. This continuity of observation, from the pre-flyby approach through the encounter and into the post-flyby phase, is what distinguishes OSIRIS-APEX from any alternative observing strategy. Ground-based telescopes can observe Apophis before the flyby, during the flyby, and after the flyby, but at an angular resolution limited by the Earth-asteroid distance, which even at 32,000 kilometers produces an object only a few pixels across in the largest ground-based instruments. The orbital tracking that ground-based telescopes provide from before and after the flyby constrains the post-encounter trajectory well, but it does not see the surface, it does not measure the rotation state continuously, and it does not detect the internal mass distribution from spacecraft orbital dynamics. OSIRIS-APEX, at a few hundred kilometers from the surface, sees the surface in detail. It tracks the rotation through the encounter. It measures the gravity field. It operates the thermal emission spectrometer when the surface temperatures are responding to the approach to Earth and recovering afterward. None of these observations is available from the ground, and none of them could have been made by a spacecraft that arrived after the flyby was complete. The pre-flyby surface map that allows post-flyby changes to be identified requires a pre-flyby map, and only a spacecraft that arrived before the encounter can make one. The OSIRIS-APEX mission is, in this specific sense, irreplaceable. No other mission profile, no other trajectory, no other timing could deliver the same scientific data set. This is what makes the fortunate confluence of the Bennu sample return timeline, the remaining fuel budget, and the 2029 Apophis flyby dates so significant. They aligned in a way that made OSIRIS-APEX possible, and that alignment will not occur again for any future asteroid encounter of comparable significance on any timeline the current catalogue reveals. What those instruments will find when they arrive at Apophis depends on the asteroid's current surface condition, something that existing observations can estimate to a degree but cannot resolve below certain spatial scales. Apophis belongs to the SQ spectral class of near-Earth asteroids, implying a surface composition broadly similar to ordinary chondrite meteorites, the most common class of stony meteorite to fall on Earth, with a mix of silicate minerals and some metal content, relatively low albedo, no significant water-bearing minerals near the surface. The internal structure is less well constrained. The light curve behavior suggests that the rotation is not perfectly uniform, consistent with either an irregular shape, a slightly asymmetric mass distribution, or a non-principal axis tumble already established before the 2029 flyby. None of the available observations can definitively resolve whether Apophis is a coherent monolith or a gravitationally bound rubble pile, the two end-member internal structures for asteroids in this size range. The distinction between monolith and rubble pile matters for more than taxonomy. A rubble pile is a loosely aggregated assembly of material held together by gravity, with significant porosity and void space between its constituent pieces. A monolith is a coherent solid body. These structures respond differently to tidal forces. A rubble pile has more degrees of freedom for internal rearrangement under stress, and its surface regolith may be more easily mobilized during the tidal interaction of the flyby. They also respond differently to kinetic deflection attempts. The momentum transfer efficiency documented for DART at Dimorphos, which turned out to be substantially amplified by the ejector plume, depends on the surface porosity and cohesion in ways that differ between rubble pile and monolithic structure. OSIRIS-APEX will begin answering the structural question immediately upon arrival, when the spacecraft's trajectory in Apophis's gravitational field starts to map the mass distribution, the spatial variation in gravity that reflects what is inside the rock. When Apophis passes at 32,000 kilometers from Earth on the 13th of April 2029, The tidal force, the differential pull of Earth's gravity across the 340-meter diameter of the asteroid, will be measurable and will do real work on the structure and rotation of the body. The Roche limit for a rocky body of Apophis's estimated density at Earth's distance is approximately 8,000 kilometers from Earth's center, or roughly 1,200 kilometers from the surface. At 32,000 kilometers altitude, Apophis will be well outside the disruption zone. The asteroid will not break apart or shed material in any catastrophic sense. But tidal forces well below the Roche limit can still alter the rotation of a non-rigid, non-homogeneous body, generating internal stresses, exciting oscillation modes, and particularly if the body has loose surface material or internal void spaces, modifying the distribution of mass relative to the rotation axis in ways that change how the body rotates after the encounter. Current models predict that the 2029 tidal interaction will measurably alter the Apophis rotation state, likely shifting the current slow, non-principal axis tumble into a different mode, with a different effective period. The magnitude and direction of the change depend on the internal structure, which OSIRIS APEX will be measuring in the approach phase while the rotation state is still evolving. The post-flyby rotation state matters for the long-term orbital calculation in a specific way. The Yarkovsky effect depends on how the asteroid is spinning. A body in steady principal axis rotation produces a Yarkovsky acceleration whose long-term behavior is straightforward to model. A tumbling body with no stable spin axis produces an acceleration whose time-average direction depends on the specific character of the tumble and whose long-term evolution is harder to predict without direct observation. If the 2029 flyby changes the tumble, the post-flyby Yarkovsky model changes with it, and the post-flyby orbital prediction for the decades following 2029 depends on having that updated model. OSIRIS APEX, there in real time, will provide the measurement. The surface of Apophis, like the surfaces of most asteroids of comparable size and type, is expected to be covered by a layer of regolith, an accumulation of rock fragments, pebbles, and fine particles built up over billions of years of micrometeorite impacts and maintained in loose mechanical equilibrium by the asteroid's weak gravitational field. Material that has been sitting in its current position for millions of years, held there by the combined effect of the feeble gravity and the friction of neighboring particles, has never experienced an external acceleration larger than roughly 1/10,000th of standard Earth gravity. During the minutes around closest approach on the 13th of April, 2029, when the tidal gradient across the asteroid's diameter is at its maximum, this equilibrium will be perturbed. The tidal force will be significantly below the disruption threshold, but it will be large enough compared to the forces that maintain the regolith equilibrium that movement is possible. Landslides may occur on slopes where the tidal acceleration exceeds the local gravitational restoring force. Boulders may shift into lower-lying regions. The fine regolith may migrate across portions of the surface, exposing material that has not seen sunlight in millions of years. OSIRIS APEX will image the surface before and after closest approach with sub-meter resolution. If surface changes occur during the flyby, and current models suggest they may, the comparison between the pre-flyby and post-flyby surface maps will document them directly. Fresh material exposed by the redistribution will have spectral properties different from the space-weathered outer layer because the effects of solar wind bombardment and micrometeorite gardening on the optical properties of surface minerals accumulate over millions of years and are not present in newly exposed subsurface material. The composition of that newly exposed material, what is inside this particular rock, chemically and mineralogically, will be one of the findings that OSIRIS APEX returns from April 2029. There is another dimension of the incompleteness problem that is worth sitting with for a moment, because it does not receive sufficient attention in the standard account of how planetary defense works. On the 15th of February 2013, at 9:22 inches the morning local time, a 20-meter asteroid entered Earth's atmosphere above the Chelyabinsk region of Russia, without warning, without any prior detection by any survey program, entirely invisible to the global monitoring network until it was already inside the atmosphere. The object exploded at an altitude of roughly 23 kilometers, releasing energy estimated at 440 to 500 kilotons of TNT equivalent. The explosion generated a blast wave that shattered windows across a wide swath of the Chelyabinsk region, and the resulting broken glass injured approximately 1,500 people, not from the impact itself, which never reached the ground, but from the atmospheric explosion's effects on buildings across an area of several thousand square kilometers. This happened on the 15th of February 2013. On the same day, Asteroid 2012 DA-14, a 30-meter object that had been known for a year, made a close flyby of Earth at about 27,000 kilometers distance, observed by telescopes worldwide and tracked continuously. 2 asteroid encounters on the same day, one watched from discovery through flyby, one undetected until the moment of detonation. The juxtaposition is striking because both objects were small. Neither approaches Apophis's 340 meters, and yet the contrast between a known and tracked flyby and a completely unwarned atmospheric explosion happening on the same calendar day makes the incompleteness of the catalogue concrete in a way that abstract statistics do not. Chelyabinsk was small enough that the planetary defense community does not routinely attempt to catalogue objects in the 20-meter class. The observation resources required to find and track the full population of 20-meter objects would be orders of magnitude beyond what any current or planned survey program can deploy. But it demonstrated something important. The atmospheric explosion of a 20-meter object injured more than 1,000 people. An atmospheric explosion of a 100-meter object at the lower end of what the survey programs are trying to catalogue would be a regional catastrophe. And a 340-meter object like Apophis does not even explode in the atmosphere. It reaches the ground. Apophis was found with 25 years of warning. Chelyabinsk gave 0. The difference between those two outcomes is the survey program, and the program is not complete. The measurement that made everything above possible, the proof that humanity could actually move an asteroid, arrived on the 26th of September 2022. At 7:14 p.m. Eastern Time, a spacecraft roughly the size of a golf cart, traveling at approximately 6.1 kilometers per second, collided with a 160-meter natural satellite called Dimorphos, which orbits a larger asteroid called Didymos, at a distance of 1.18 kilometers. The collision was deliberate. The spacecraft was DART, the Double Asteroid Redirection Test, and its single purpose was to demonstrate whether a kinetic impactor could produce a measurable change in the orbit of a natural asteroid. The measurement came from ground-based observatories monitoring the Didymos system's mutual eclipse pattern before and after the impact. Dimorphos and Didymos periodically pass in front of each other from Earth's perspective, producing a brightness variation with a period equal to Dimorphos's orbital period around Didymos. Before the DART impact, that period was 11 hours and 55 minutes. After the impact, photometric observations accumulated for weeks, and the fitted period was 11 hours and 22 minutes. A change of 33 minutes. The minimum success threshold for the mission was 73 seconds. The result was 25 times larger than the threshold. The reason the result exceeded expectations was not that DART transferred more momentum than its mass and velocity implied. DART itself transferred exactly the momentum that its mass and velocity would predict. What exceeded expectations was the momentum carried away by the ejector plume. The material excavated from Dimorphos's surface by the impact launched outward in the direction of DART's approach, each ejected particle carrying a small amount of momentum in the direction opposite to its travel, and therefore pushing the asteroid forward in a secondary propulsion effect. The asteroid moved more than DART alone could push it, because the impact disturbed the surface in a way that generated its own propulsion. For the first time in 4.5 billion years of solar system history, a human object had changed the orbit of a natural body in space. The result was measured, confirmed independently by multiple facilities, and published. What DART demonstrated at Dimorphos establishes a proof of concept that the planetary defense community had been waiting for, and it also establishes limits that are directly relevant to the Apophis case. Even though Apophis currently requires no deflection, Dimorphos was 160 meters in diameter. Apophis is approximately 340 meters, roughly twice the diameter. Kinetic energy scales with mass, and mass scales with the cube of the relevant dimension. Apophis carries approximately 8 times the mass of Dimorphos. Moving Apophis by the same fractional velocity change that DART achieved at Dimorphos would require 8 times the impact to mass at the same velocity, or some combination of higher velocity and improved targeting geometry that reduces the required impact to size. But the more fundamental variable than impact to size is lead time. A kinetic impact changes the asteroid's velocity by a small amount. For DART at Dimorphos, the velocity change was measured in millimeters per second. That small velocity change, applied years before a projected close approach, accumulates into a large positional change. The trajectory diverges from the unperturbed path, and by the time the close approach date arrives, the asteroid is thousands or millions of kilometers from where it would have been without the deflection. The further in advance the deflection is applied, the larger the final displacement for the same velocity change. Applied 10 years before the relevant date, a fraction of a millimeter per second is enough to shift a trajectory by multiple Earth diameters. Applied 1 year before, the same velocity change shifts the position by a fraction of an Earth diameter. Applied a month before, the displacement is negligible. The window closes, and it closes according to orbital mechanics, not according to funding decisions or political timelines. For any hypothetical future impact scenario involving Apophis or any other asteroid, the question of whether a deflection mission can succeed depends on when the threat is confirmed and how much time remains to reach the asteroid and apply the necessary velocity change. Apophis, discovered 25 years before its closest approach, represents the ideal case. Maximum lead time, maximum options. Other asteroids in the catalogue, particularly the ones not yet found, may not provide the same lead time. The catalogue that exists today reflects the work of several decades of survey programs, and it is significantly incomplete. Current estimates from the survey network suggest that between 40 and 60% of near-Earth asteroids in the potentially hazardous size range, 140 meters and above, remain undiscovered. The population that has not yet been found is not smaller than the population that has been found. It is comparable in size. Several thousand objects that qualify as potentially hazardous by the definition the field uses are orbiting through the same inner solar system, crossing the same orbital paths, untagged, untracked, and absent from every database on Earth. The incompleteness is not a consequence of insufficient effort. It is a consequence of geometry. Ground-based programs observe at night from Earth's surface, looking outward away from the Sunday objects in Arton-type orbits. The orbital family that includes Apophis spends significant portions of their orbits in the sunward direction, where they are hidden in the glare and inaccessible to ground-based telescopes during the hours when observation is possible. Objects approaching from the sunward direction can arrive with very little warning, detected only when they emerge from the glare, which may be days, hours, or in some cases minutes before closest approach. NASA's NEO Surveyor mission, an infrared space telescope designed to operate from the L, one Lagrange point between Earth and the Sun, imaging the inner solar system from an angle unavailable from the ground, is intended to close this gap, finding the majority of the remaining large near-Earth object population within 10 years of full operation. The catalogue after NEO Surveyor will look substantially different from the one that exists today. Some of those new entries will have impact probabilities attached to them when first discovered. Some will require the same kind of extended, careful calculation that Apophis required over 17 years, We found Apophis because a survey telescope swept the right section of the Arizona sky on the right night in June 2004. The asteroids still absent from the catalogue are not less real for being unfound. The Apophis discovery had an effect on the planetary defense field that was not fully anticipated in December 2004. It accelerated the development and formalization of procedures, communication protocols, and coordination mechanisms that had previously been informal or incomplete. Before Apophis, the planetary defense community had no tested protocol for announcing a high-probability impact scenario to the public. The Torino Scale existed as a communication framework, but it had never been tested against a real case at the level it would need to function at. The coordination between independent calculation groups, JPL, NEODIS, and the ESA Coordination Center, had not been stressed by a real case where three groups were computing the same probability and the public was watching the results update. The procedures for handling media inquiries during a genuine alarm had not been worked out at the operational level. The 6 weeks from the 23rd of December 2004 to the final clearing in late January 2005 were the first real test of all of these systems simultaneously, and the field learned from it. The communication challenges, the difficulty of explaining a growing probability as an artifact of improving knowledge rather than a worsening threat, the problems with how media translated technical uncertainty into plain language headlines led directly to improvements in how the field describes impact probabilities publicly and to the development of more refined guidance for communication during alarm periods. The coordination between independent groups, which had worked well but had not been tested under pressure, was exercised and its robustness confirmed. The result is that the planetary defense community is more prepared for the next Apophis-level alarm than it was in December 2004, not only because the computational methods are better, but because the human and institutional systems for responding to such an alarm have been tested, evaluated, and improved. This is a form of learning that only happens under real conditions, and it only happened once, with Apophis, in December 2004 and January 2005. The next time a near-Earth object achieves a non-zero impact probability that holds through additional observations, the institutions involved will be able to draw on the Apophis experience. The communication procedures, the coordination protocols, the knowledge of what the public misunderstands and what explains it well. This is not a negligible inheritance. The people who have been doing this work deserve a moment of consideration. Because planetary defense tends to be described in terms of institutions and probabilities, and the human texture of the work does not often come through. The centers that maintain the catalogues and perform the orbital calculations, JPL's Center for Near-Earth Object Studies, the Minor Planet Center at Harvard-Smithsonian, ESA's Planetary Defense Office, Space.is at the University of Pisa, employ dozens of specialists whose professional lives have been spent at the boundary of what instruments can resolve and what mathematics can determine. The survey programs that find the asteroids run with small teams of astronomers and software engineers, operating telescopes across multiple sites, processing data volumes that no individual person could review manually, generating the stream of discoveries and positional measurements that feeds into the catalogue continuously. The work is steady and methodical and mostly quiet. The December 2004 alarm was exceptional. Most of the catalogue entries have impact probabilities that dissolve within days or weeks of discovery, as the additional observations arrive and the orbits are refined. The standard day in a planetary defense institution is not emergency response. It is precise measurement, careful computation, and the gradual, patient accumulation of an orbital knowledge base that extends across the entire inner solar system. The urgency is structural rather than felt at any given moment. The consequence of doing this work badly is not an inconvenience or a missed deadline, but something that cannot be taken back. The people who spent 17 years on the Apophis orbital determination, Tholen, Giorgini, Chodas, Yeomans, Farnokia, Bernardi, and the many others who contributed observations and analysis, across the full span of the problem, were not, in most of those years, working under conditions of visible alarm. They were performing a series of patient, technically demanding measurements, updating a calculation, submitting it to the catalogue, and waiting for the next observational window. The drama of December 2004 receded into years of quiet precision work, ending not with a sudden revelation but with a radar campaign in January 2021 and a catalogue update on March 5. That is what solving the problem actually looked like. In the weeks before the 13th of April 2029, the night sky will begin to change in a way that most observers will not notice unless they know what to look for. Apophis will be approaching Earth from the south, moving along a trajectory that brings it up from the southern celestial hemisphere into the northern one over the weeks leading up to closest approach. At magnitude 10 or 11 inches, the final month before closest approach, still below naked eye visibility but within reach of a backyard telescope, it will already be moving noticeably against the star background from one night to the next. Amateur astronomers with modest telescopes will be able to track it weeks before the flyby, watching the point of light accelerate night after night as the approach geometry compresses the angular motion across the sky. In the days immediately before April 13, the asteroid will brighten through magnitude 8 and then 7 and then 6, the threshold of naked eye visibility, and in the final hours before closest approach it will brighten rapidly as the distance drops from tens of thousands of kilometers to the 32,000 at minimum range. The apparent magnitude at closest approach, approximately 3.4, reflects not just the asteroid's size but the geometry of the encounter. A 340-meter body at 32,000 kilometers is faint by any comparison to the Moon, which is 3,500 kilometers in diameter at 384,000 kilometers. But at that distance, it is bright enough to be clearly visible, clearly moving, and clearly unlike any star the observer has ever watched. In the hours following closest approach, the asteroid will fade again as it recedes, dimming back through magnitude 5 and 6 as the geometry opens up, moving southward again toward the horizon for observers in the northern part of the viewing corridor, and continuing to be visible at southern latitudes for longer. By the end of the 13th of April 2029, for observers anywhere in the primary viewing corridor, Apophis will be back to near telescopic visibility and receding on its post-flyby trajectory. A trajectory that will be measured by OSIRIS APEX in real time, constrained with the precision the mission was designed to provide, and published to the scientific community in the days and weeks that follow. The night will last a few hours, as all nights do. What it will leave behind is a measurement history that the field does not yet have, and that no other event in the near-term future will provide. The night of the 13th of April 2029 will look different from different places on Earth. And the differences say something worth considering. From Rome, the asteroid will be visible in the southern sky after sunset, moving steadily northeast, at a pace that most observers will first notice by the way it shifts position relative to the surrounding stars over 5 or 10 minutes of watching. It will be above magnitude 3, brighter than the dimmest stars visible from a city park with street lighting, accessible from suburban rooftops, and easily visible from any location outside the city centre. The surrounding stars will provide a natural reference frame, and the motion against them will be unmistakable to any patient observer. From Cairo, the asteroid will transit nearly overhead at closest approach, and from this geometry the angular speed will be slightly higher. The point of closest approach will appear almost directly above, and the motion along the sky will be near its maximum apparent speed, the most dramatic possible viewing angle for an observer on the ground. From Western Africa, the Sahel, coastal West Africa, the equatorial nations south toward Nigeria and Cameroon, the viewing conditions will be similar to Cairo's in geometry, but often better in atmospheric clarity, with the asteroid crossing a sky free of the urban light pollution that affects European observers. Some of the clearest views of the 2029 flyby will be from locations that do not typically feature in the narrative of planetary science. From observers in places that have been doing astronomy for as long as any civilization on Earth, watching the same sky under better conditions than most of the world's professional observatories. From locations outside the primary viewing corridor, North America, East Asia, Australia, the asteroid will either be below the horizon at closest approach or will be visible at a lesser magnitude, earlier or later in the encounter window. These observers will not see the peak of the flyby, but they will see it on the approach or departure phase, and at those phases the asteroid will still be brighter than most stars in the evening sky. Across all of these locations, one thing will be consistent: the knowledge that the moving point of light is a 340-meter rock, named for the serpent that devours the sun, found in the Arizona desert in the summer of 2004, calculated to a 2.7% impact probability in December of the same year, tracked for 17 more years, cleared on March 5, 2021, and now passing at 32,000 kilometers altitude, having made millions of orbits around the sun in the 4.5 billion years before anyone thought to look for it. Now consider what the 13th of April 2029 will actually be. The viewing geometry means that Apophis will be accessible from a band of Earth's surface spanning Europe, North Africa, West Africa, and Western Asia. Roughly 3 billion people in the viewing corridor on a night when the moon will be waning and conditions will be acceptable across most of the coverage zone. The asteroid will appear at approximately magnitude 3.4, brighter than most stars in the Big Dipper, clearly visible from any location, with a reasonably dark sky, and detectable even from suburban areas where light pollution limits what can be seen. It will not look like a meteor, brief and gone in seconds. It will move at roughly the apparent angular speed of the International Space Station, steady and deliberate, crossing a degree of sky every few minutes, visible for several hours around closest approach. 3 billion people will know what they are watching. They will know its name, its history, the December 2004 calculation that produced 2.7%, the Torino Scale level that had never been reached before, the 17 years of orbital refinement, the Arecibo campaigns, the Yarkovsky measurement from Tholen's optical baseline, the Goldstone observations in January 2021, the March 5 announcement that closed the catalogue entry for the first time. They will be watching something that, in all the previous history of large asteroid close approaches on this planet, has never once been watched by anyone who knew what they were seeing. Every previous close approach of an object of this size occurred without human knowledge, or with knowledge too imprecise to interpret. Everyone. Something that old had never been seen coming. Until now. Now picture the actual moment. The moment on the 13th of April 2029 that is approaching, whether we are prepared for it or not. It is evening in Europe and North Africa. The asteroid is already visible in the darkening sky, moving from south to north at a pace that requires a few minutes of patient watching before the motion is unmistakable against the background stars. In observatories across the viewing corridor, automated tracking telescopes are following it at high magnification, feeding imagery to networks that will archive every second. In the control room of the Deep Space Network, operators are monitoring the telemetry stream from Osiris Apex, a few hundred kilometers from the asteroid's surface, transmitting data at the highest rate the mission design allows. Surface imagery, spectral maps, altimetry readings, rotation state updates. On the surface of Apophis, at this moment, the tidal gradient of Earth's gravity is at its maximum. The surface material is responding to forces it has not experienced in millions of years, settling into new configurations, shifting in ways that the pre-flyby surface map will not show and the post-flyby surface map will record. Osiris Apex is imaging it, section by section, in real time. Below, on the planet, 3 billion people are looking up at a faint moving star and knowing what it is with a precision that took 17 years to achieve, knowing the name of each scientist who ran the calculations, knowing the number that alarmed the field in December 2004, knowing the date of the March 5 announcement that closed the last formal threat assessment. They are watching the first large asteroid in human history to be seen coming, tracked continuously from discovery to encounter, characterized by a spacecraft alongside it and understood in detail before the event that made the understanding necessary. This is the moment that the 13th of April 2029 always was, from the night of the 19th of June 2004, when David Tholen looked at the result and did not move. Before the spacecraft transmits its first images from close proximity, and before the 3 billion observers on the ground reach for whatever they will reach for to mark the occasion, there is one more thing to say about what the 2029 flyby means for the asteroid itself. Not for the orbital calculation, and not for the observers, but for Apophis as a physical object in the solar system. Apophis has been making its 323-day orbit for 4.5 billion years. During those 4.5 billion years, it has experienced micrometeorite impacts at regular intervals, slowly grinding its outer surface into the regolith layer that covers it now. It has absorbed solar radiation and re-emitted it as heat every day of every orbit, slowly drifting under the Yarkovsky push, accumulating millions of kilometers of positional offset from where a purely gravitational orbit would have placed it. It has been shaped by the cumulative effect of ancient collisions that determined its current elongated, irregular form. Its rotation state reflects the history of those impacts, the tidal interactions it has experienced over its long history, and the internal redistribution of mass that has slowly settled the body into its current tumbling motion. In all of those 4.5 billion years, Apophis has never passed this close to Earth. The 32,000-kilometer approach on the 13th of April 2029 will be, as far as the orbital record can establish, the closest the asteroid has been to our planet in its entire history. Though the history is so long that complete certainty about ancient close approaches is unavailable, the event is, for the asteroid, unprecedented in the sense that any body's approach to the range where another body's gravity does substantial work on it is unprecedented if it hasn't happened before. The tidal forces will compress the near side of the asteroid more than the far side during the approach and stretch them during the departure. The regolith will respond, the rotation will change, and when Apophis has passed and is receding back through the geostationary ring and out into the outer reaches of its orbit, it will be a slightly different rock from the one that was approaching, with a different rotation state, perhaps a redistributed surface, and a post-encounter trajectory that will be immediately measured by OSIRIS APEX and documented more precisely than any asteroid's trajectory has ever been documented from a companion spacecraft. After billions of years of quiet orbit, the rock is finally being watched. It does not know this, but we do. After the 13th of April 2029, the Apophis story does not end. It changes character. The orbital determination produced by the post-flyby tracking data, from OSIRIS APEX in proximity, from the global network of radar and optical observatories monitoring the approach and departure, from the long baseline positional measurements that will accumulate in the months and years following the encounter, will be the most precise determination of any near-Earth asteroid orbit ever achieved. Not because the measurement techniques will be different from what exists today, but because the event itself provides a geometric baseline that cannot be replicated from any distance. A spacecraft measured the trajectory through the keyhole period from a few hundred kilometers away, and the resulting position and velocity data at the moment of closest approach constrain every subsequent orbit with a precision that 17 years of Earth-based tracking approached, but could never fully reach. Whether that precision reveals anything requiring attention in the decades and centuries beyond 2116, any close approach that the pre-flyby determination could not rule out, but the post-flyby data now constrains, is a question that will be answered by the analysis. And the analysis will not be complete until the data are in hand. What will be known immediately, transmitted back from OSIRIS APEX, almost from the moment of closest approach, is what the asteroid actually is. Its shape and size refined to centimeter precision, its rotation state documented through and after the tidal interaction, its surface composition mapped across the full disk, its internal structure implied by the gravitational field measurements. This dataset will become the reference for every subsequent assessment of Apophis, and, because Apophis will be by then the best characterized potentially hazardous asteroid in the solar system, for the broader class of objects that share its orbit type, size range, and dynamical environment. What OSIRIS-APEX learns at Apophis in 2029 will be what the field draws on for the next generation of assessments. In the years before the 2029 flyby, Apophis is doing what it has always done, orbiting the Sun in a 323-day ellipse, crossing Earth's orbital path twice per circuit, approaching the inner solar system during the part of its orbit closest to the Sun, and retreating through the outer portion of its range during the rest. It passes through our neighborhood on a schedule determined by the geometry of its ellipse and the geometry of Earth's, and most of those passes are at distances large enough to attract no attention. Tens of millions of kilometers rather than tens of thousands. What changed in June 2004 was not the orbit. It was the knowledge. Before the Spacewatch detection, Apophis was doing exactly what it did after. Orbiting, crossing, approaching, retreating. The asteroid was not a threat in December 2004 inches, any sense that it had not been a potential threat in December 2003 or December 2023. The orbital mechanics that produced the 2.7% impact probability had been governing the asteroid's trajectory for the entirety of its existence. The probability did not emerge in response to being discovered. It was always there. It simply was not known. This is worth holding, gently, because it changes the way the story feels. For the billions of years before the 19th of June 2004, Apophis was making the same approach to Earth that it will make in 2029. Not the same close approach, but the same kind of approach, the same orbital geometry, the same relationship to our planet's gravitational field. Nothing protected us during those billions of years except the orbital geometry itself, which happened not to produce an intersection. And nothing will protect us in 2029 except the same geometry, now calculated with a precision that allows us to confirm in advance that the geometry is favorable. The knowledge did not change the physics. The knowledge changed what we could do about the physics. Before 2004, we could not have detected a Yarkovsky drift that was pushing the orbit toward a keyhole. We could not have calculated the keyhole probability. We could not have sent a spacecraft to accompany the close approach. The 17 years between the discovery and the flyby were the window in which the knowledge translated into capability, a window that, for most of the solar system's history, did not exist, and that, for most of the potentially hazardous asteroids not yet found, still does not exist. The 13th of April, 2029 arrives, because the orbital geometry produces it. The knowledge of what will happen on the 13th of April 2029, the cleared probability, the confirmed close approach distance, the spacecraft on approach, arrived because someone pointed a telescope at the right section of the Arizona sky on the right summer night and ran the calculation. The full catalogue of potentially hazardous asteroids, the 2,300 known objects that meet the size and orbital proximity criteria, contains, in addition to Apophis, a broad range of objects at different stages of orbital characterization. Most have been observed for too short a time to have precise orbits, and their impact probabilities, where non-zero, are typically at the level of statistical noise. Uncertainties so large that the probability reflects ignorance of the orbit rather than genuine knowledge of a threat. Most will be refined away to zero as additional observations accumulate, but a small subset of the catalogue is in a different position. Objects that have been observed long enough to have reasonably precise orbits, and whose orbits are precise enough to reveal that close approaches are possible on specific future dates, but not yet precise enough to rule out the narrow keyhole corridors that would make those close approaches threatening. These are the objects that look, in the current data, like early phase Apophis, not at 2.7%, but at 1 in 10,000 or 1 in 50,000, with the critical question being whether additional observations will push the probability to zero or hold it at a level that demands a response. The lesson of Apophis for these objects is that the answer can take years to arrive, and that the years are not wasted waiting. They are spent accumulating precisely the kind of observation baseline that allows the Yarkovsky effect to be measured from the residuals, which is the technique that ultimately resolved the Apophis problem in 2021. Every year of additional tracking for any object with a residual non-zero probability is a year in which the baseline lengthens and the Yarkovsky signal becomes more extractable. The Apophis story, in this sense, is not just the history of one asteroid, it is the development and validation of the method that the field will use for every subsequent candidate that holds a non-zero probability long enough to require the same kind of careful, extended answer. And so what does this rock represent? Not for the planetary defense calculation, but for what it required humanity to do. Apophis required 17 years of sustained, methodical, technically demanding work across multiple countries, multiple institutions, and multiple generations of instruments. It required Tholen's optical baseline spanning more than a decade, Giorgini's trajectory modeling, Chodas's keyhole calculations, Yeomans's institutional steadiness through the December 2004 alarm, Bernardi's precovery search that started the whole chain, Farnokia's January 2021 analysis that ended it. It required the 2003 Golivka-Yarkovsky detection in science to have already validated the method, and Arecibo to have been operational in 2008, and Goldstone to have remained operational after Arecibo was gone, and OSIRIS-REx to have had enough fuel left after Bennu that the spacecraft could be redirected to a second target before anyone was certain a second target would be needed. What came out of the 17 years is not just a cleared probability table and a spacecraft on approach. It is a practiced, validated, end-to-end process for detecting, characterizing, and responding to this category of threat. A process that had never been run at full length before Apophis, that was refined at every stage by what the asteroid required, and that will be the default procedure for the next candidate that achieves a non-zero impact probability and holds it long enough to demand a serious answer. Something that old had never been seen coming until now. And what we built to see it, track it, calculate it, and fly a spacecraft to accompany it. That is the part that belongs to us, and the part that will matter when the next alarm sounds. There is a particular quality to knowledge that has been earned through patient, sustained, technically demanding work over a long period of time. A quality different from knowledge acquired quickly, or from insights that arrive without the years of preparation that make them meaningful. The Apophis orbital determination is this kind of knowledge. It required 17 years. It required instruments that were old enough to have decades of operational history, and institutions stable enough to maintain continuous attention across changes in administration, funding, personnel, and circumstances. It required a physical effect, the Yarkovsky drift, to have been described by a Russian engineer in a 1900 pamphlet that almost no one read, to have been rediscovered several times, validated experimentally in 2003, and then applied to a newly discovered asteroid 18 months later. It required the asteroid itself to have been in a large enough size class to warrant the observation resources and close enough to Earth's orbit to provide enough close approaches for the radar campaigns to reach, and slow enough in its rotation to generate a measurable Yarkovsky acceleration rather than the averaged-out accelerations of a fast spinner. None of this was arranged. The orbital mechanics produced it. The human institutions happened to be in a configuration that could respond. What the 13th of April 2029 represents, beyond the physical encounter, beyond the record close approach, beyond the spacecraft data and the cleared probability and the 3 billion observers, is the completion of a specific human achievement. A 340-meter rock was found, tracked, calculated, and understood in the decades before its closest ever approach to Earth, and a spacecraft was placed alongside it to witness the encounter and extend the knowledge beyond what Earth-based instruments could reach. This has never happened before. It has happened once, with this asteroid, on this timeline, and the knowledge it produces. The physical characterization of Osiris Apex, the post-flyby orbital determination, the validated methods for Yarkovsky measurement and keyhole calculation will be what the field carries forward when the next large asteroid holds a non-zero impact probability long enough to demand the same kind of answer. Something that old had never been seen coming, until now, and what we do with the seeing, the spacecraft we send, the catalogue we build, the network we maintain, the next discovery we make, the night before, everything might change. That is the part of this story that has not finished. The universe has been producing close asteroid approaches for 4.5 billion years. It will produce them for the remainder of the Sun's lifetime, which is another 5 billion years at least. In the very long view, in the deep time that this channel tends to inhabit, the 13th of April 2029 is one encounter among uncountable many, neither the first nor the last, neither the closest on geological timescales nor the largest object to pass near the third planet. What is singular about the 13th of April 2029 is not its physical scale, it is its place in the brief history of a species that learned to watch. For 4.5 billion years, the solar system arranged its geometry without any observer capable of recording what was happening. Close approaches, keyholes, orbital resonances, gravitational encounters. The first instrument capable of detecting an asteroid was not built until the 19th century. The first systematic search for near-Earth asteroids did not begin until the 20th. The first potentially hazardous asteroid to be found, tracked over a long baseline, and characterized in enough detail to allow confident long-term predictions, was Apophis in 2004. In the 4.5 billion years of this planet's history, the 13th of April 2029 is the first time a large rock in a close approach trajectory to Earth will be accompanied by a spacecraft watched by 3 billion people who know what they are looking at, and understood in advance with the precision that the calculation of its future requires. That is not a small thing. That is, in a specific and measurable sense, the first time the planet has been genuinely prepared for an encounter of this kind. Sleep now. If the sky is clear where you are, in the years to come, look up on the 13th of April 2029. You will know what you are looking at, and it will not know you are there, but you will be. If your eyes feel heavy now, let them close. The universe will still be here when you wake up. So will we. Good night.